There is a substance on our planet that holds a universe of energy within its core. It is born from the explosive death of ancient stars, scattered across the cosmos, settled into the crust of our world. We call it uranium. The very name can conjure images of immense power, mushroom clouds, the quiet, persistent hum of a city at night. This material is not inherently good or evil. It is simply an element, a fundamental piece of the cosmic puzzle. The truth about its handling, its transformation, its use is far more nuanced than the stark images we'd expect. The story of enriched uranium is a human story of fear, curiosity, strict rules, and our ongoing quest to harness the atom responsibly. Myths are powerful. They are simple. They are sticky. They are easy to remember. They are easier to repeat. When it comes to enriched uranium, the myths are persistent and frightening. One common myth: any enrichment facility is secretly a bomb factory. The same process makes fuel for a power plant. The myth says a flip of a switch produces weapons material. That blurs the line between different levels of enrichment. It also ignores the immense technical hurdles to weapons-grade material. It creates a picture of constant, imminent danger behind factory walls. But that's an oversimplification of a highly controlled process. Another myth focuses on worker and community safety. Pop culture shows people in hazmat suits. Pop culture shows corridors glowing an eerie green. Pop culture shows constant catastrophic exposure. The story becomes, living near uranium is a death sentence. That ignores decades of research. It ignores the development of stringent safety protocols. It overlooks constant health monitoring. It overlooks protective shielding. It overlooks redundant safety systems. The reality inside these plants is routine and regulated. There's also the myth of simplicity and secrecy. Some imagine enrichment in a hidden basement or in a small clandestine workshop. That fuels fears of rogue states or terrorists building a bomb. To understand the reality, we must start with the basics. Let's talk about what uranium enrichment actually is, in simple terms. Uranium is a naturally occurring heavy metal found in rocks all over the world. When miners dig it up, it is composed of several different types of atoms, called isotopes. Think of them as siblings in the same family. They are all uranium, but they have slightly different properties. The vast majority, over 99%, is an isotope called uranium-238. A tiny fraction, about 0.7%, is a different isotope called uranium-235. It is this rare sibling, uranium-235, that is special. It is fissile, meaning its core can be split apart to release a tremendous amount of energy. For most of the world's nuclear power reactors, that natural 0.7% concentration of U-235 is not quite enough to sustain the controlled chain reaction needed to generate heat and produce electricity. The process of enrichment is simply the act of increasing the percentage of U-235 in a batch of uranium. So how do factories actually perform this incredible sorting task? While the detailed physics is complex, the high-level concepts are understandable. You cannot just pick the atoms out with tiny tweezers. Instead, engineers have developed a few large-scale industrial methods. These are not simple machines. They are housed in enormous, highly secure buildings and require a massive amount of infrastructure and energy to operate. They are designed to exploit the tiny mass difference between the heavier uranium-238 atoms and the slightly lighter uranium-235 atoms. It is a brute force process that has to be repeated thousands upon thousands of times. One of the most common methods used today is the gas centrifuge. First, the solid uranium is converted into a gas. The gas is pumped into tall, spinning cylinders, centrifuges. The cylinders spin at incredibly high speeds, faster than the speed of sound. Centrifugal force pushes heavier U-238 outward, while lighter U-235 stays closer to the center. Internal scoops draw off center gas, now slightly richer in U-235. That gas goes to the next centrifuge in a cascade to be separated again. Another, older method is gaseous diffusion. It also starts by turning uranium into a gas. The gas is forced under high pressure through porous membranes. Inside a uranium enrichment facility, safety is not an afterthought. It is the fundamental principle around which everything is built. The primary goal is to protect the workers, the public, and the environment from the specific hazards of the material being handled. This involves multiple redundant layers of safety protocols, engineering controls, and continuous monitoring. Workers are the first line of defense and the first priority for protection. They receive extensive training on handling procedures, emergency response, and the nature of radiological hazards. They are required to wear personal protective equipment, which can range from standard lab coats and gloves to specialized respiratory gear, depending on the specific task they are performing. The facility itself is designed with safety in mind. Engineering controls are built directly into the process to contain the uranium material. The immense power contained within enriched uranium means these facilities don't operate in a vacuum. They're among the most heavily scrutinized industrial sites on Earth. A multi-layered web of oversight national authorities, international bodies keeps a constant watch. The first and most direct layer is national governments. Each country with enrichment has a dedicated regulatory agency, for example, the U.S. Nuclear Regulatory Commission, NRC. These agencies write the rules, license facilities, conduct inspections to ensure plants run safely and securely. National regulators hold immense power. They set standards for worker safety, environmental releases, physical security, accounting for nuclear material. So, what is the final picture? The reality of uranium enrichment is sober and complex. It is not the stuff of spy thrillers, but a serious, highly technical, and intensely regulated industry. The fear that a power plant's fuel facility could suddenly explode like a bomb is a misunderstanding of physics. Low-enriched uranium simply cannot do that. The real dangers are more subtle. The risk of accidental release of radioactive material, the risk that the technology could be diverted for military purposes. These are not trivial risks, and they are precisely why the industry is wrapped in such thick layers of safety protocols, security measures, international oversight. The system is designed with the assumption that things can go wrong, and it builds in redundant checks to prevent that from happening. The good news is that for decades, this global system of controls has been largely successful. The vast majority of enriched uranium produced in the world is used peacefully to generate clean, reliable electricity for billions of people. The International Safeguard System, led by the IAEA, has proven effective at detecting undeclared nuclear activities and building confidence between nations. The safety record of modern enrichment plants is strong, a testament to the stringent engineering and regulatory standards that have been learned and applied over many years. This does not mean the system is perfect or that we can become complacent. Vigilance is the price of safety.